Uh,
So what do we got tonight? What'd you guys go over today?
we did 6-5 theorems about roots of polynomial functions.
Okay. Rational root theorem. All right. This is what I've been warning you about for a long time. Let's see. So do you have a specific one you want to work on? In other words, you know what the rational root theorem says? Or what it means?
I don't know it. Like, we don't memorize them in class. We just...
Okay, let's look at this first one that she's got here. There's really only one thing you got to memorize. When a polynomial is in standard format like this, if there is a rational zero, and that's a big F, then its numerator must be a factor of the constant, and its denominator must be a factor of the coefficient of your leading term. So factors of 5 are plus and minus 5 and plus and minus 1. Notice that it's plus and minus. So the numerator could be plus or minus 5 or plus or minus 1. And the denominator has to be plus or minus 3 or plus or minus 1. So what are our possible rational roots? Do all combinations. In other words, it can be plus or minus 5 over 3 or plus or minus 5 over 1. It can be plus or minus 1 over 3 or plus or minus 1 over 1. So we end up with the following possibilities. And just for your info, it's all of them are always plus or minus. All of these are rational. Okay? And it figures that there's going to be a rational root. And why? Because there are 3 solutions to this. Because it's a third-degree polynomial. Well, there might be some imaginary solutions, but they would come in pairs, always. Okay. So if there's 2 imaginary solutions, there's only one other solution left, and it would also have to be rational because irrational solutions also come in pairs. In other words, if you have a solution 2 plus root 15 to a polynomial, then this is also a solution. In the same way that if you have 2 plus I, then you know that 2 minus I is also a solution. These come in pairs. So it's virtually impossible, and probably completely impossible, for this not to have a rational solution. Because there's no way you could have 2 rationals and 2 imaginary. That would be 4. So we know that most likely we do have a rational, and it's one of these 8 numbers. So what do we do now?
That's it.
That's where you're stuck?
Yeah. No, that's all we have to do.
No? Oh, really? You don't have to actually discover which one is the 0?
Not on all of them.
Okay, how would we do that? In other words, for this problem here, how would we determine which of these 8 possible answers is the solution?
Plug it into the calculator.
Yeah, or just plug it in here. And if I'm going to use a calculator, I can use any of them. But if I'm going to do it by hand, I'm going to look at plus and minus 1 first. Okay, so if I look at plus 1, I got 3 minus 1 minus 15 plus 5. That doesn't work. If I look at minus 1, I got minus 3 plus 1 minus plus 15 plus 5. That doesn't work. So that's not one of our solutions. So the next one I would probably try, if I'm doing it by hand, is 5, because I see a lot of multiples of 5 up here. But 3 times 125 minus 25 minus 75 plus 5, that's not going to work either. So plus 5 doesn't work. You get the hang of this? Now,
Yeah.
the reason they taught you, or the reason they put so much effort into teaching you synthetic division
Yeah.
is for these kind of problems. In other words, the better way to determine whether these are solutions is let's synthetically divide. I tested plus 5. I'm going to try minus 5. And I need to get a 0 for it to be a solution. So go through me. Help me with this.
You bring down the 3. 3 times negative 5 is negative 15. You get negative 16. Times negative 5 is 80.
All right.
And then
Clearly, this isn't going to work either. It's not 0.
yeah.
Okay? So it has to be 0 remainder for it to be a solution. So now we've tried plus or minus 1. We've tried plus or minus 5. Let's do a synthetic using a fraction that we have not ever tried. Let's try the easiest one, plus 1/3.
Okay. 1. And then 0. Then 0. And 15. Negative 15. Negative 5. 0.
Bingo. There's our solution. So x equals 1/3 is one solution to that problem. Now, how would we find the other in other words, if at some point, surely they're going to want you to find all the zeros.
Mm-hmm.
So what would we do as our next step to find the other 2 zeros? We don't know at this point whether they're real or complex. But what do I have to do? Notice that when I synthetically divided this by 1/3, what I got was the result of that division.
Mm-hmm.
In other words, now I know what my factors are for this polynomial. They're x minus 1/3. That's one of them. And what's left over? This quadratic. 3x squared minus 15. And that actually factors more. In other words, I can take a 3 out of there, so I got x minus 1/3 times 3 times x squared minus 5. I can leave it like that, but x squared minus 5, I can apply the difference of squares to that, even though it's not perfect squares. I don't care if it's not perfect squares. That's x minus root 5 times x plus root 5. So your 3 solutions are x equal 1/3, x equal root 5, and x equal minus root 5. Those are your 3 zeros of that polynomial.
Okay.
Okay? And that's why synthetic substitution works so good, or rather synthetic division, because not only do you determine whether or not one of these is a solution, but you get the resultant quadratic automatically as your answer. So you know what the other factor is also. And that's the way you would have to do it. In other words, if somebody told you right off the get-go that x equals 1/3 is one solution, the way you would get the rest of it is to divide that polynomial by x minus 1/3. And you would get 3x squared minus 15 as a result. And so those are your factors. And then if this can be further factored, do it. If it can't be, then it's called an irreducible quadratic, and that would be your final answer.
Okay.
Okay. All right. Do you have one you want to do that maybe isn't in her thing?
I don't.
Okay. Have you done both of these in class?
Yeah.
All the way through?
No, not all the way through.
Oh, the question is just list all possibles. If I go down another page, am I going to run into other problems here?
You should.
Okay. Which ones have you not done?
Number 2.
Okay. And in this case, we're supposed to find all possible roots.
Mm-hmm.
And I presume these are not calculator problems?
I think they are. I'm not sure.
I'm guessing they're not, because if they were a calculator problem, you wouldn't have to learn all this rational root theorem. Right? In other words, if you could use the calculator, you just put it in there, analyze, find the zeros. It's going to give you all 3 solutions. So this is titled Using the Rational Root Theorem, so it's not a calculator problem. So first of all, let's list all possible roots.
P plus or minus. Well, P is 10.
Well, P are factors of 10. P isn't 10. The rational root, which I can write as P over Q, merely says that P are possible P's are all of the factors of 10. Possible Q's are all of the factors of the coefficient of the x cubed term. So what are the factors of P? Or not P, but the factors of the coefficient.
Plus or minus 10, plus or minus 1, plus or minus 5, plus or minus 2.
And the bottom?
Plus or minus 1.
So now what are all the factors? And they're just the top, right? In other words, it's that over that, that over that, that over that, or that over that. And since it's 1, those are my possible solutions.
Mm-hmm.
Okay? So next step.
Synthetic division.
There's a hint, yeah. In other words, we have 8 possible solutions that we have to try, one by one. That's the only way to do it, if you have to do it by hand. And the advantage of doing synthetic division is that when we find our solution, we're going to have the remaining quadratic staring at us. So we don't have any dummy variables that we need to deal with, so we put them all up there. What's the first one? Let's try.
1. Yeah, 1, -1.
Okay, so let's try negative. The other beauty is that when you're trying synthetic, you don't need to rewrite everything over again. Oh, I went through it I know are you comfortable with your synthetic division?
Yeah, for the most part.
So you don't mind me doing this quickly?
No.
That's not it? So that's not it. This has promise. Okay. So I've got 0. Now how can I write that third degree polynomial as a linear factor times a quadratic? There's the linear factor, there's the quadratic. What's the linear factor going to be?
X minus 5?
Minus 2.
Minus 2. Ah, that's right.
We were using 2 when we got this 0. Now what's the quadratic factor?
X squared. Minus 5.
Uh-huh. Okay. So now we're close to having all that they ask. What are my 3 solutions?
X equals plus or minus 2. And no?
Just 2.
Just 2?
Yeah, because what I'm doing is I'm solving this equation. X minus 2 equals 0. So X equals 2. Only 2. Now I got to solve the other factor. This is the other factor. So X squared minus 5 also could be 0. So X squared equals 5. And what does X equal?
Root 5. Plus or minus root 5.
Whenever you take the square root of both sides of an equation, remember your plus and minus. All of my students miss it. If I'm going over a quiz with a student and I see that he's missed this problem, I tell him in advance, I know what you did. You left out the plus or minus, and I'm always right. I don't know how to get it through. I wish I had some little song I could sing to you that would make you remember to always add the plus or minus when you have to take the square root of both sides of an equation. So, what are my 3? Well, you know what they are. It's x equal 2, or x equal plus root 5, or x equal minus root 5. Notice that my irrational solutions came in pairs, as they always should. It's irrational because it's root 5. In other words, we would never have found the root 5 solution using the rational factor theorem. The rational factor theorem, or the rational root theorem, only finds rational solutions. It's never going to find that root 5. So the only way for us to solve this problem is by finding the one rational solution, dividing, coming up with the resultant quadratic, and then solving for the other 2 irrational solutions.
Okay.
Okay? Let's do one more. Let's do 3. Let's have you do it from the get-go. Make sure I can read it right. 3x cubed plus x squared minus x plus 1.
That's all we just did. No.
I think we did that one there.
Okay.
Yeah. First step.
P and Q.
Right. Our first step is to see what are the possible rational solutions. So what are they?
Would be plus or minus 1/3, plus or minus 1. And just do 1.
I always try the easiest ones first.
And 3. 1. It's not that.
No. So let's try minus 1. Okay. So we found it. I don't need to check the others. So x equals minus 1. In other words, there's not really any point in me going through the process with the other possibilities. Once I've found the one rational solution, usually the other two are irrational, but how can I now finish the problem? So let's write this polynomial as the product of a linear factor and a quadratic factor.
Okay.
So what's the linear factor?
X minus 1.
It's x minus a minus 1. So it's x plus 1 is the linear factor. What's the quadratic factor?
X squared. This one would be minus 1?
3x squared.
Oh, well, okay.
Minus 2x plus 1. In other words, I'm getting those coefficients from that.
Okay.
Okay? That's the beauty of synthetic trial and error, is that when we find the right answer, we have the other quadratic that I can now factor using regular techniques. And in fact, this does have, I think this is 3x. No, it isn't, is it? No, it doesn't factor nicely. So, what now?
Quadratic formula.
Yeah, plug that into the quadratic formula to find the two solutions, real quick.
Equals 2 plus or minus 4 minus...
Read it out loud and I'll write it as you're reading it. What's minus b?
I got x equals 2 plus or minus square root of 4 minus 12 all over 6.
Okay, let's simplify that.
Negative 8, then 6, then x equals 2 plus or minus I.
Hold on, 8 can be simplified.
Yeah. 2 root 2.
Mm-hmm. Where's the I go? Like that?
It doesn't matter as long as it's not under the sign.
Right. Well, it actually kind of does matter. You want your answer to be in A plus BI format. You're right that at this point it doesn't really matter. I can put that I anywhere as long as I don't put it in the radical. Mm-hmm. But I want to reduce this. In other words, this isn't my final answer. I want to get it in that kind of format. So what's my next step?
Divide by 6.
Well, let's simplify. We got to split this into two fractions. So there's the real part of the solution, and there is the imaginary part of the solution. So what does that look like?
X equals 1/3 plus 2 root 2I over 6.
The 2 and the 6 can be simplified.
1 and 3.
So what is my rest of it?
1 root 2I over 3.
How about just root 2 over 3I? In other words, now we have it in the precise exact format. A plus BI. A is 1/3, B is root 2 over 3.
Okay.
And those are our three solutions. Our first one was x equal minus 1. There's our three solutions. Isn't that fun? Imagine how hard it's going to be when they give you one that has a 12 there and a 12 there. Now you got 8 possible factors in the numerator and 8 possible factors in the denominator. You're going to end up like with 30 different possible things that you have to just do trial and error to solve.
Awesome.
And you thought quadratics were hard. Now, most people think quadratics are hard if you have to use the quadratic formula, but they're nothing compared to cubics. All right, Silas. I will see you at your next session. I don't know if your mom's doing next Monday night or not. I'll let her take care of that on her own. Oh, this is just, oh, this is only Tuesday.
Tuesday.
I'm talking to you tomorrow night then. Sorry. All right. Good night.
Night.